This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on the archive paper Pointer Networks, which introduces a novel neural architecture for learning conditional probabilities of output sequences. These sequences have elements that are discrete tokens representing positions within an input sequence. This is a significant departure from traditional sequence-to-sequence models. What are the key limitations of existing approaches that this paper addresses?
Existing methods like sequence-to-sequence models and neural Turing machines struggle with problems where the number of target classes at each output step depends on the variable length of the input. This is a common characteristic of combinatorial optimization problems, such as sorting variable-size sequences. The output dictionary size is not fixed a priori, making standard approaches inapplicable.
The paper proposes a solution using a neural attention mechanism. How does this differ from previous uses of attention in sequence-to-sequence models?
Instead of using attention to blend encoder hidden units into a context vector at each decoder step, pointer networks, PTR nets, use attention as a pointer to directly select an element from the input sequence as the output. This allows the model to handle variable-sized output dictionaries effectively.
The paper demonstrates PTR nets on 3 geometric problems: convex hull, Delaunay triangulation, and the traveling salesman problem, TSP. What were the key findings regarding the performance of PTR nets on these tasks?
PTR nets significantly outperformed sequence-to-sequence models, both with and without input attention on these tasks. Importantly, they generalized well to input sequences longer than those seen during training, demonstrating the model's ability to learn underlying patterns rather than simply memorizing examples. Even on the computationally complex TSP, PTR nets produced competitive approximate solutions.
The paper mentions that the computational complexity of the PTR net is ONN at inference time. How does this compare to the complexity of exact algorithms for these problems? What are the implications?
Exact algorithms for convex hull and Delaunay triangulation have a complexity of ON log n, while TSP is NP hard. The O imputation of PTR nets represents a trade-off between computational efficiency and solution accuracy. While not providing exact solutions, PTR nets offer a computationally feasible approach to approximating solutions for these complex problems, especially for smaller problem sizes.
The paper highlights the importance of the order in which inputs are presented to the encoder. Can you elaborate on this observation and how it influenced the model's design?
The order of input presentation significantly impacted the performance, particularly for the convex hull problem. When points on the true convex hull appeared late in the sequence, accuracy suffered. This observation led to the incorporation of the attention mechanism, allowing the decoder to access the entire input sequence at each step, improving performance and robustness.
The authors mentioned that the architecture and hyperparameters weren't extensively tuned. What are the potential implications of a more thorough hyperparameter search and architectural exploration?
A more thorough search could potentially lead to improved performance, especially on larger problem instances. Exploring different LSTM architectures, attention mechanisms, or even incorporating other neural network components could further enhance the model's capabilities and generalization ability. The current result even without extensive optimization. The paper discusses the use of beam search during inference. How does this impact the computational cost and the quality of the solutions obtained? Beam search helps to find the highest probability output sequence, but it increases the computational cost. The beam size is a trade-off between computational resources and the quality of the solution. A larger beam size explores more possibilities, potentially leading to better solutions, but at a higher computational cost. In the TSP example, the beam search was constrained to only consider valid tours, further impacting computational costs.
The paper mentions the use of special tokens and ARG to represent the beginning and end of sequences. What is the purpose of these tokens and how do they contribute to the model's functionality?
These tokens act as delimiters, signaling the start and end of the input and output sequences. They provide crucial context to the recurrent neural network, allowing it to distinguish between the encoding and decoding phases. Without these tokens, the model might struggle to identify the boundaries of the sequences, leading to errors in prediction.
The paper emphasizes that PTR nets are specifically designed for problems where outputs are discrete tokens corresponding to positions in the input. What are the limitations of this approach, and what types of problems are not well suited for PTR nets?
The primary limitation is the restriction to problems, where the output is a sequence of indices directly referencing the input. Problems requiring continuous outputs or outputs not directly related to input positions would not be suitable. For instance, directly predicting coordinates instead of indices might lead to blurry predictions and a loss of the constraint that outputs map back to the inputs.
The paper mentions the use of different algorithms to generate approximate solutions for the TSP for larger N. How did the choice of these algorithms impact the training data and the model's performance?
Using different approximation algorithms for generating TSP training data for larger N introduced variability in the quality of the training examples. This variability could affect the model's ability to generalize and find optimal or near optimal solutions. The results showed that even training on data from less accurate algorithms still yielded competitive results, highlighting the robustness of the PTRNet architecture.
The paper concludes by suggesting future work on applying PTR nets to other problems like sorting. What are some other potential applications of this architecture beyond the three geometric problems discussed?
The architecture's ability to handle variable length output dictionaries makes it suitable for various sequence-to-sequence tasks where the output length depends on the input. Examples include tasks involving graph manipulation, program synthesis, or any problem where the output is a permutation or subsequence of the input.
The paper mentions that the model generalizes beyond the maximum lengths it was trained on. Can you elaborate on the mechanisms that might contribute to this generalization ability?
The generalization ability likely stems from the model learning underlying relationships and patterns in the data rather than simply memorizing specific input-output pairs. The attention mechanism allows the model to focus on relevant parts of the input, regardless of its length, contributing to this generalization. The use of recurrent networks also allows the model to capture sequential dependencies.
Finally, what are the key takeaways from this research, and what are its potential implications for the field of neural network-based combinatorial optimization?
The key takeaway is the introduction of a simple yet effective architecture, PTR nets, that addresses the challenge of variable length output dictionaries in sequence-to-sequence learning. This opens up new possibilities for applying neural networks to a wider range of combinatorial optimization problems, offering a data-driven approach to approximating solutions for computationally complex tasks. The results demonstrate the potential of using attention mechanisms as pointers to select elements from the input, leading to improved performance and generalization.
The paper mentions the use of an LSTM with 256 or 512 hidden units. How does the choice of hidden unit size affect the model's capacity and performance? What are the trade-offs involved?
A larger number of hidden units increases the model's capacity to learn complex patterns and representations. However, it also increases the computational cost and the risk of overfitting. The choice of 256 or 512 units represents a balance between capacity and computational feasibility. A more thorough hyperparameter search could potentially identify an optimal hidden unit size for different problem sizes and complexities.
The paper uses stochastic gradient descent with a learning rate of 1.0. How sensitive is the model's performance to the choice of learning rate? What are the potential consequences of using a learning rate that is too high or too low?
The learning rate is a crucial hyperparameter that significantly impacts the model's training process and performance. A learning rate that is too high can lead to oscillations and prevent the model from converging to a good solution. A learning rate that is too low can result in slow convergence and potentially get stuck in local optimus. The choice of 1.0 in this paper might be suitable for the specific problem and dataset, but it's important to note that optimal learning rates can vary significantly depending on the model architecture, dataset characteristics, and optimization algorithm.
The paper employs L2 gradient clipping with a value of 2.0. What is the purpose of gradient clipping, and how does it help to stabilize the training process?
Gradient clipping is a regularization technique used to prevent exploding gradients during training, a common issue in recurrent neural networks. When gradients become too large, they can destabilize the training process, leading to numerical instability and poor performance. Gradient tightening limits the magnitude of the gradients, ensuring that they remain within a reasonable range, thus promoting stable training and preventing divergence. The value of 2.0 is a heuristic choice, and the optimal clipping value might need to be adjusted based on the specific model and data set.
The paper generates 1 million training example pairs. How does the size of the training dataset affect the model's performance and generalization ability? What are the trade-offs involved in choosing a larger or smaller dataset?
A larger training dataset generally leads to better model performance and improved generalization ability. However, it also increases the computational cost of training and might require more resources. The choice of 1 million training examples represents a balance between the desired performance and the available computational resources. The authors observed overfitting in some simpler tasks, suggesting that a smaller dataset might suffice for those cases.
The paper mentions that the model was trained with a batch size of 128. How does the batch size affect the training process and the model's performance? What are the considerations in choosing an appropriate batch size?
The batch size affects the efficiency and stability of the training process. Larger batch sizes can lead to faster convergence, but might require more memory and computational resources. Smaller batch sizes can introduce more noise in the gradient updates, but might lead to better generalization and escape from local optima. The choice of 128 represents a compromise between these factors. The optimal batch size can vary depending on the model architecture, data set size, and available computational resources.
The paper uses random uniform weight initialization from NADA 0.08 to 0.08. How does the choice of weight initialization affect the model's training and performance? What are the potential consequences of using different initialization strategies?
Weight initialization is crucial for the success of training deep neural networks. Poor weight initialization can lead to vanishing or exploding gradients, hindering the training process. The choice of uniform initialization from NADA 0.08 to 0.08 is a common practice, aiming to provide a reasonable starting point for the weights. Other initialization strategies, such as Xavier or Hay initialization, might be more suitable for certain architectures or activation functions. The choice of initialization strategy can significantly impact the training speed and the final model performance.
This has been a thorough discussion of the Pointer Networks paper. Thank you.